Okay, before we do the next problem, just while we're sort of, just to break up the problems, the next problems are much more complicated. So let's take a quick break and look at Newton's second law and see if what we're learning here has told us anything more about the Principia here. Because if someone was asking, can we use impulse equals ma delta t with kinematics? Well, you kind of can, because that's kind of what Newton was talking about here. So we look at a second law. What was the second law say? Oh, there's Latin, there's there we go. There's that. Oh, we didn't watch that. Oh, wait, crap, where'd it go? Oh, I didn't put the translation of the second law. Where's the second law? Oh, no, I have to translate it live. Oh, God. Oh, never mind. The second law is related to momentum. Never mind. Let's see. Let me just write it down. Newton's second law. We don't need the words. All right, so here it is. Here it is in Latin. I really do need someone to translate it now. The modus proportional to the life of the mortician was impressed by the fire, and the second line, I don't know what the hell it's saying. Okay, so Newton's second law is sum of the forces external equals ma, but he didn't say that. He didn't say, oh, the force is equal to the sum of the forces is ma, because we could look at this and say, what is A? A is mass times dv dt. But if you know a little bit about derivatives, you know you could put a constant inside of there, right? Constants just go in and out of a derivative. They don't matter. So we could say it's dmv dt. Ooh, what is that? That's dp dt. So if you read actually what he said, he's really talking about the state of motion again. He says the state of motion changes when there is a force impressed thereon or something like that. Okay? So technically, this is an approximation. Technically. Because you could imagine a case where mass is changing. And then if mass isn't constant, you have to have a term of v times dm dt plus m times dv dt. So you say, well, if mass is constant, surely you throw that one out and you just have this, and that's just F equals ma. But in a sense, F equals ma is already an approximation. It's already incorrect. Okay? If you think this way, you'll mess yourself up and you'll get some weird inconsistencies, and it's because nothing can really change mass in terms of fundamental particles. Like the mass is always constant. So if you start changing the mass of something because it's like leaking sand, it's sort of a made-up homework problem thing. And it usually works. But you can turn yourself in knots over it. But I mostly just wanted to point out that really, you might see somebody write some of the forces. You might see a coffee cup. This is some of the forces as dp dt rather than ma. And this is the reason. It's really what he meant. Okay. That was the useful sidebar there. Here we go. Okay. It was worth it. Okay. Okay. Let's see. So we've done that.